Welcome to the description of equilibrium. So now we're going to look at ideal gas equilibria. So remember, we're still looking at a chemical reaction. So we have A being converted into B, and B can then convert back into A. So we're going to start by looking at ideal gases. If A and B are both ideal gases, then we can use this equation. So the chemical potential of our substance, either A or B, is equal to the chemical potential of that substance when it's pure. So this is the chemical potential in the mixture, by the way. So the chemical potential when it's pure plus R times T times the natural log of the pressure of that component A or B in the mixture divided by the pressure of that component when it's pure. So now remember from the last video that the Gibbs energy of reaction is equal to the difference between the chemical potential of B and the chemical potential of A. So the difference in chemical potential of our products minus reactants. So now we can write the chemical potential of B in the mixture as the chemical potential of B when it's pure plus R times T times the natural log of the wave pressure of B divided by the wave pressure of B when it's pure minus the chemical potential of A while it's pure plus R times T times the natural log of the vapor pressure of A in the mixture divided by vapor pressure of A when it's pure. And now remember the difference here. We can do some rearranging here. So the difference here, that's delta RG, so the Gibbs energy of reaction. So here we have Gibbs energy of reaction from our pure substances. So that's this term, delta RG naught, plus R times T times the natural log of pressure of B divided by pressure of A. So note that here we've used the mathematical rules for logarithms to get rid of or to move the pressure of A below the pressure of B here. All right, so now we can denote the ratio of partial pressures as Q, so we're going to plug that in here. So we've changed, basically the only thing we've done here is replace in the natural log, we've replaced pressure of B over pressure of A with this value Q. So Q now is our reaction quotient. So this ranges from 0 when the pressure of B is 0, note that that's pure A, to infinity when the pressure of A is 0, and thus we have pure B. So you've probably seen, or I hope you remember seeing Q before in reaction quotient when discussing things like equilibria. So it's the same Q here in this case. So the standard reaction Gibbs energy, so delta RG naught, is defined as the difference in standard molar Gibbs energies for our reactants and for our products. So that value is equal to the molar Gibbs energy, standard molar Gibbs energy of B minus the standard Gibbs molar energy of A, and that's the chemical potential of B when it's pure minus the chemical potential of A when it's pure, so again in their standard states. So note here that our delta R now has our normal meaning of the difference between two values, right? So the delta RG naught here is a difference between two G naught values, basically, right? So this is different. It's not the derivative that we saw earlier. So in practice now, we relate the standard Gibbs energy of reaction to the standard Gibbs energies of formation of our reactants and products, which we symbolize here as delta F G naught B and delta F G naught A. And at equilibrium, our Gibbs energy of reaction is 0. We know so that if we denote our ratio of partial pressures K, because at equilibrium our reaction quotient Q becomes K, the constant. So now we're denoting our ratio of K instead of Q. So now we can say that 0, because we know that the Gibbs energy of reaction is 0. 0 is equal to the Gibbs energy of reaction, the standard Gibbs energy reaction plus RT times the natural log of K. Again, here K has the same form as Q, except that we're constraining it to work or to be at equilibrium. So if Q is equal to K, then we're at equilibrium. So that then rearranges to this, so we move the RT natural log of K to the other side, that makes it negative. So now we can say that the standard Gibbs energy reaction is equal to minus RT ln K. And so now, finally, we have a link between our standard Gibbs energy reaction and our equilibrium constant K. So over here, to the right here, is a plot of our Gibbs energy on the vertical axis as a function of the extent of reaction xi, and that means that we have some mixing, and so we have some minimum Gibbs energy. So we have some minimum in here. So note that as we go from our Gibbs energy of our reactants up here to the Gibbs energy of our products down here, that's without any mixing being taken into account. We have this red curve. Right? As we convert from reactants to products, we're just changing the ratios of how much of our reactants we have and how much of our products we have. Well, we know that our Gibbs energy of our reactant is higher, the chemical potential of our reactant is higher than the chemical potential of our product. If that's not the case, then the reaction doesn't proceed, or doesn't proceed very far. But once we include the mixing, so the mixing gives us this sort of curve, and so once we include the mixing there, once we've added this blue curve to this red curve, we get this second blue curve, and so we have a minimum somewhere around there, maybe. And so note that this minimum in Gibbs energy is arising from the mixing of our two gases. Right? As we mix our gases, we're increasing the entropy of our system. So again, let's look at our A goes to B reaction. If only the enthalpy is mattering here, then the enthalpy and thus the Gibbs energy would change linearly from pure reactants to pure products, as we saw on the last slide. And the slope of this line is delta RG naught, so the standard Gibbs energy of reaction at all extents of reaction, so it doesn't matter where along that xi curve we are, or along the xi axis we are. And this means that the minimum value of Gibbs energy would then occur at either pure reactants or pure products. But that's not what happens, because we need to factor in entropy. So when we factor in entropy, then we have an additional contribution to our Gibbs energy from the mixing of our two gases. So remember that the Gibbs energy of mixing is the number of moles of gas N times R times T. So that N is the number of moles of total number of moles of gas, not the number of moles of either one component. So nRT times the mole fraction of A times the natural log of A plus the mole fraction of B times the natural log of B. And now this contribution is concave upwards with a minimum value and so that's that mixing curve that I showed on the plot a few slides back. And that means that now our total Gibbs energy is then the sum of these two terms, and our equilibrium lies at the sum of the total of those two. And again, from this equation, which we've already derived earlier, now we can see that when the Gibbs energy, the standard Gibbs energy reaction is positive, so greater than 0, that means that K has to be less than 1. And at equilibrium, then the pressure of A is greater than the pressure of B. That means we have more A around than B. We have more of our reactant around. If the Gibbs energy of reaction, the standard Gibbs energy of reaction is less than 0, then K is greater than 1. At equilibrium, the pressure of A is less than the pressure of B. B is favored, so we have more B around. So in this case, in order for this to be true, the chemical potential of A has to be less than the chemical potential of B. And thus we have to be increasing the Gibbs energy as we react. If the chemical potential of A is lower than the chemical potential of B, we expect that to have mostly reactant, mostly A. If the chemical potential of B is lower than the chemical potential of A, then we expect to have mostly product. And so then B will be favored. So let's extend this argument to a general reaction, so not just two substances involved. So now we can express a reaction symbolically like this. So we have 0 is equal to the sum over all components J of stoichiometric coefficient, sort of Vj times J, capital J. So this J denotes all the substances involved in the reaction. The Vj are the stoichiometric coefficients. So remember now that the stoichiometric coefficients are positive for products and they're negative for our reactants because they're being consumed in the reaction. So now we can define our extended reaction psi such that a change in the extended reaction by delta xi results in a change in amount of these species J by our stoichiometric coefficient Vj times delta xi. And now we can show that our reaction Gibbs energy at any arbitrary stage is then the reaction Gibbs energy reaction is equal to the standard Gibbs energy reaction plus R times C times the natural log of Q. And now, with our standard reaction Gibbs energy calculated from standard Gibbs energies of formation, then we get delta Rg naught is equal to the sum over all the products of the stoichiometric coefficient of our product times Gibbs energy formation of that product minus sum over all the reactants, a similar term for the reactants. And so now we can then combine these together to get a similar sum over all of our components J of the stoichiometric coefficient, either positive for products or negative for reactants, of the Gibbs energy of formation of our component J. And now our reaction quotient Q has the form the activities of the products divided by the activities of the reactants. And each of our species here, so each activity is raised to the power of the stoichiometric coefficient. So the activity raised to the our stoichiometric coefficient. Note that in this case, the powers are all positive, even for the reactants. So now we can use our capital pi symbol here to denote a product. So just like how capital sigma denotes a sum, capital pi denotes a product. So now we have Q is equal to pi over, so product over all substances J, out of all of our components J, of the activity of J to the power of Vj. So this V here, this stoichiometric coefficient, is either positive for products or negative for reactants. Right? So if it's negative, then we're basically dividing by that by the positive exponent term. So again, here note that because our reactants have a negative stoichiometric coefficient, the V, they appear in our denominator of Q. And also remember that the activity of a pure liquid or solid is 1, and that means that they don't influence Q. Because if we're multiplying by 1, we're dividing by 1. It's not going to change the value of Q any. So now at equilibrium, the slope of G is 0, and that means we can say that the Gibbs energy of reaction is 0 at equilibrium. And now we can define our equilibrium constant, K, just the same as we did for Q, except that now we're putting on this constraint that it must be at equilibrium. So K is sort of a special case of Q, the case where we're at equilibrium. The reaction is at equilibrium already. So note that now, from now on, we're no longer going to explicitly use our equilibrium subscript when we're talking about K and the burden is on U, to remember that we have to use equilibrium values for whatever is in there. So for this sort of term, we're going to drop the parentheses equilibrium, and you need to remember that the activity here is the activity at equilibrium. The stoichiometric coefficient doesn't change at equilibrium. So now our equilibrium constant expressed in terms of activities or of fugacity for gases is called a thermodynamic equilibrium constant. And note here that since our activities are dimensionless, K and thus Q must also be is dimensionless. They're both dimensionless, K and Q. So in practice, usually we replace our activities by our molalities, by replacing our activity of J with a fraction here of the molality of J, our component J, divided by 1 molal. So this B naught is 1 mole per kilogram. Or we replace it with, or we replace our activities with molar concentrations, so molarities. Again, replacing our activity of J with concentration of J divided by C naught. So C naught is 1 mole per liter. Or sometimes we use partial pressures instead of fugacity. Again, replacing the activity or fugacity with this sort of fraction of the pressure of our component divided by P naught, where P naught is 1 bar. So in these cases, now our resulting expressions are just approximations. So they're no longer exact, so you shouldn't treat them as being perfectly mathematically exact. But if we're using activity, these expressions that we've developed, that we've derived, are in fact exact. If we replace the activity with either molality, molar concentration, or partial pressures, then they're just approximations. So now we can replace Q with K, and we get the Gibbs energy of reaction is equal to standard Gibbs energy of reaction plus R times T times the natural log of K, our equilibrium constant. And we know that at equilibrium, the Gibbs energy of reaction is 0, so we can replace, we can plug a 0 in there, and now we have the 0 is equal to the delta RG naught plus R times T times natural log of K, and then we can move RT natural log of K to the other side and get this equation. So now delta RG naught is equal to minus RT ln K. So know that this is similar to that derived earlier for our equilibrium between two ideal gases. But in this case, now our reaction is no longer confined to two ideal gases. It applies to any reaction, right? So we've basically derived the same thing as earlier, except now this equation applies to a generic reaction. We haven't constrained ourselves to ideal gases anymore. So now this equation allows us to calculate the equilibrium composition of any reaction from a table of thermodynamic properties. So we can figure out what K is given a number of thermodynamic properties. So if we can figure out what delta RG naught is, then we can figure out what K is at some temperature. So equilibrium constants expressed in terms of activities are exact, but usually it's useful to relate our equilibrium constants to concentration. So again, we can formally relate our concentration to activity using our activity coefficients. So the activity of component J is equal to the activity coefficient, gamma J, times the mole fraction of J. Or we could say it this way: the activity of J is equal to the gamma J, the activity coefficient of J, times the ratio between the molality and the standard molality, so one molal. Or we could say the activity of J is equal to the molar concentration of J divided by C naught. So C naught again was the 1 molar, so 1 mole per liter. Again, we're basically just trying to get rid of the units, so that activity is unitless. Again, this gamma j is the activity coefficient, chi j is the mole fraction, the lowercase b is the molality, and the j in brackets is our molar concentration, so the molarity. So if now we want to find our equilibrium composition expressed in terms of molalities for an equilibrium, again, this box is supposed to have a double-headed arrow there. So if we have A plus B reacting to give us C plus D, we can write, as long as all four of our substances here are solutes, we can then write that the K is equal to the activity of C times the activity of D divided by the activity of A times the activity of B, which now we can separate out, and we can write the molalities, the ratio between the molalities and the ratio between the activity coefficients. And that then gives us two terms. So K using the activity coefficients and a K using the molalities. So to a first approximation for our equilibrium constant K, K gamma is assumed to be 1. Right? We're assuming that our activities are, or that ratio between our activities is 1. So note that this is really only valid at low concentrations. So if now we wish to express our equilibrium constant of a gas phase reaction in terms of molarities instead of partial pressures, we can now replace the partial pressure Pj with a concentration of J times R times T if our gases are ideal, and that means that now our equilibrium constant is then equal to once we replace our partial pressure of J with our concentrations, that's now equal to this. So now we have our product over all substances of our concentration to the power of our stoichiometric coefficient Pj here, and then times again the product over all of our substances of R times T divided by P naught. Again, the P naught was to get rid of the pressure units, so it's 1 bar. Again, to the power of Vj, so the stoichiometric coefficient. And now we can define our dimensionless equilibrium constant, Kc, like this. So now we have Kc is equal to that first product term that we had on the last slide. And now our equilibrium constant K is equal to Kc times the second product term. So now we can write delta V, so the change in our stoichiometric coefficient, our change in number of moles of gas in this case, is the number of moles of gas, so the stoichiometric coefficient of all of our products minus the stoichiometric coefficient of all of our reactants. So this now gives us this. So note that now we've replaced that product with our change in number of moles of gas, stoichiometrically at least, and now we've combined together the R and C and C naught and P naught terms to give us temperature over 12.03 K. Note that this K is not the K there, right? This is an equilibrium constant K, and this K here is a unit Kelvin. So that's just there to get rid of the Kelvin units that we'll plug in for our temperature. So now let's look at the molecular interpretation of our equilibrium constant. So remember our Boltzmann distribution of molecules over the available states in our system, of our system that's composed of both reactants and products. So we have some reactant A that has some available energy levels, and some product B that has some available energy levels. And we have some Boltzmann distribution of states amongst those possible levels. So when atoms can exchange bonded partners, like in a reaction, our available states of our system include arrangements in which the atoms are present in the form of reactants and in the form of products. And this means that these arrangements have characteristic sets of energy levels, but our Boltzmann distribution only explains the energies, not the identities. And so our atoms are distributed over the energy levels according to our Boltzmann distribution. So at some given temperature, there will be a specific distribution of populations of energy levels, and thus some specific composition to our reaction mixture. So, if our reactants and products have equally spaced energy levels, then the more abundant species is the one with the lower set of energy levels. So in the figure that I showed earlier, that was species A. Right? A had lower energy levels than B did, but they were spaced equally. But if the higher energy set has a smaller spacing between the energy levels, then there are some temperatures at which it's more abundant. There are some temperatures at which it's not, but there are some temperatures at which it is more abundant. So this effect is due to the increased entropy of the set with a smaller spacing between the energy levels. So remember now that the delta RG naught, so the standard Gibbs energy reaction, is equal to the standard enthalpy of reaction minus the temperature times the standard entropy of reaction. And also remember that our delta RT naught here is equal to minus RT ln K. And that means now if we solve this, set the two equal to each other, because they're both equal to delta RG naught, and solve for K, now we get K is equal to E to the power of minus delta RH naught over RT times E to the power of delta RS naught over R. So note that now a positive enthalpy of reaction, so an endothermic reaction, results in a smaller equilibrium constant, and thus an equilibrium composition with our reactants are dominating. But a positive entropy of reaction results in a larger equilibrium constant, and thus an equilibrium composition favoring our products over our reactants. So that was the description of equilibrium.